It is my pleasure to introduce Alejandro Benito-Santos, Assistant Professor at the UNED in the Department of Computer Languages and Systems. Alejandro's research lies at the intersection of natural language processing, human-computer interaction, information visualization, and digital humanities. He holds a PhD in computer engineering and has previously been a Margarita Salas and Juan de la Cierva postdoctoral researcher in the NLP IR group at UNED. Today he will give a talk entitled Learning with Annotator Disagreement and Perspectivism in STS, where he will discuss how disagreement, ambiguity, and diversity of perspectives in language data can be better represented and exploited in natural language processing models. So please join me welcoming Alejandro.
Thank you very much. Thank you very much. So good morning, everyone. Buenos días. Okay, so thank you, Mikel, for the introduction, and thank you to Tracasa also for having me here today. It's my pleasure to introduce a little bit of my recent work in the area. So as Mikel already said, my areas of expertise, I did my PhD on human-computer interaction and visualization, visual analytics, interactive analytics, etc. And then I moved to an NLP group because in my thesis I applied a few methods that were related to information extraction, information retrieval, automatic hypothesis extraction from scientific corpora, etc. So then I was really interested in NLP, and also there were many groups in Spain on visual analytics, and I had to leave my alma mater, the University of Salamanca, so I said, well, why not? Let's try NLP because it's also on the news, etc. So let's get into it. So I was there first as a Margarita Salas, then Juan de la Cierva, and now I got more into what's being called human-centered NLP, which is basically the intersection between human-computer interaction and NLP, right? But okay, enough about me. Today I come here to plant a little seed in your brains. My intention here today is that you won't see AI evaluation and NLP evaluation in the same way as you probably have seen it so far. So you probably have been given what I call the blue pill, right? So there are certain assumptions that we have related to how AI systems are evaluated. So for example, you all assume that a ground truth exists and it is unique, right? So there is only one single truth that all AI systems should try to optimize for, right? And also, you are accustomed to see rankings, so saying which system is better than other on certain tasks. And also, it's like, well, you get the data, you train the system, and then you test it and call it a day, right? It's like if you get a score and say, my system A is better than system B. But the story behind it is a little bit more nuanced. There are certain things that we'll be looking at today that are really important regarding the construction of the benchmarks and how annotations sometimes are filtered, removed, averaged, or aggregated. And that removes certain variability. And we need to be really aware of that. The red pill that I'll be giving you today goes another way. And is, for example, when you see an ordinal scale, for example, in annotation experiments, we will focus today on STAs. How many of you know about the STS task in NLP? How many of you have heard about this task? 1, 2, 3. Well, because you read the paper, right? Okay, silly me. Anyways, if you pay attention when you were reading the paper, you would have seen that the ratings, so the similarity of the two sentences, is given by ordinal ratings, right, on a scale. So you have a rubric, and then many people, well, not many, just 5, annotate the pair, and then you derive a ground truth from it, a ground truth. We'll go back to that. So my intention today is that when you see someone averaging an ordinal scale, you will raise your eyebrow, like, this is probably not right. Or maybe we should check if it is right, at least. Well, we are moving more, this is a change in paradigm, and we are moving more towards the comparison of actual distributions rather than single point estimates. This is what the talk is more or less about, okay? So we'll see if at the end I've succeeded or not. So my intention is that today, this paradigm, at least you know about it and try to apply it if possible in the future. Okay, this is STS task. So here you have a pair of sentences, and let's do an experiment live. You have sentence A, which says a man is playing the guitar. And sentence B says someone is playing a musical instrument. And you have the rubric. This is kind of like summarized or abbreviated, but basically the scale says from 0 to 5, 0, they are completely different in meaning, and 5, they are completely equivalent in meaning. So very quickly, how many of you say this is, well, a 3, for example? Roughly equivalent. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 people. How many of you would say this is mostly equivalent? Okay. 1, 2, 3, 4, 5, 5. Completely equivalent? No? And share some details? Okay. So much less than 9. Okay, so the peak is at the number 9, and then you see like there are like people who approximate this 3 value, which was the modal value in the distribution. But there are many truths, right? And who is right? Of you, who is right? Nobody's right, completely right, because everybody's got different perception of the similarity between the semantics of these two sentences. Let's continue with this is a first thing, but in STS, all the variability, like people who said 4, people who said 2, they are kind of removed. So the systems don't learn about these people. They learn a mean, an average, and that's a problem. And for many reasons, and I'll explain some of them today. That's my intention. Let's continue with experiments. I love experiments, so let's see. Can you pull out your phones, please, and scan the QR code? Let's do it live. So you will see 3 pairs of sentences. This is the first one. US fast food workers plan nationwide strikes over minimum wage. And B, fast food workers strike for higher pay. Let me know if it works. You need to vote in all the 3 of them, okay? Unfortunately, I cannot plot the distribution live because I was expecting to use my laptop. But anyways, I can show you in the screen from my laptop. Right. Oh my God. Okay, I see people voting in the first question. Don't overthink it. Just the first impression that you got on the similarity. Could you vote for the 3 of them? Yes? Just one? Only one? It's blocked. Ah, okay. Sorry, I told you this was an experiment. Experiments can go wrong. So, right. Let's see. 24 of 29. Now? Oh, sorry. No, 2. Okay, now 2, sorry. It's the first time I'm using this. So you are my subjects today. A dog runs through the water, a dog runs through the grass. Okay? That's it. Last one, 24, 25. Mostly there. Okay. Now with the last one. Egypt announces end to a state of emergency, and Egypt declares month-long state of emergency. Done? Everybody? Yes? Okay. 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 So this is the actual data from the annotation experiment, the original annotation experiment for the STS task, okay, in 2017. And you see, like, all the annotators say it was a 4. Like, they are mostly equivalent. And I don't know if you can see it, but these were your results in live. So the majority of people are here in this classroom are aligned with the actual annotators from the original experiment. Oops, sorry. Yeah. Okay, but still, 7 of you said roughly equivalent. 2 of you said share some details, and 2 of you said completely equivalent. Okay, but in the original experiment, the ground truth for this question was 4. So any response that an AI system trained on the original data would give would leave like 9, 11 of you unsatisfied. It doesn't align with your preferences. That's bad. Next slide. Here, the distribution is a little bit more broad. There's more disagreement, and it goes, well, the actual mean of the experiment was 2.4. Whatever that means, we will reflect on that for a second. Whatever that 2.4 means, but because no annotator actually said 2.4. And what did you say? So for example here, oops. So the modal value in the original experiment was 3, and here nobody said 3. The original annotators were English speakers, were from different countries from you. They had different understanding of the language, probably. So this kind of makes sense, but still, we can see that it is quite spread, this distribution, okay? But still, you can see that there is a lot of disagreement in this pair of sentences. So whenever this is used to train a system, it's using a mean value of 2.4. But what does that even mean? What does 2.4 mean? Because it's not something that we can select. So there is not something inside of us that actually maps semantic similarity to a value of 2.4. That's a problem too. We will see why. Okay? And now, to finish with the experiment, oh, this is more alike, right? So, okay. So 2 out of 3, you were in line with the original annotator. So more or less works. But we will see that this is the problem, that in the end, all these systems that are trained in this way more or less work, more or less for a majority of people. But what happens with people who think differently or who have other values? That's a problem. And that's a problem that is being researched a lot in these days, right? Okay. Thank you for participating in my little experiment. More or less worked. So I think I can reuse it in the future. Okay, so the same problem, right? 2 distributions, different values. So for example, the bimodal distribution shows that 3 people said 0, 3 people said 5, and still you get the same mean value, right? Obviously a problem. So this is the traditional view, and you've probably seen it, that you aggregate. You can do several techniques to aggregate. You can use majority voting. You can use averages. You can use other methods. But you are always assuming that there is only one correct answer for a given item. And we assume that this agreement actually comes from bad annotators or bad guidelines. If you read, we will go to that later, but if you read some of the survey on soft evaluation, there are certain aspects of annotation that can be seen as real disagreement, but we will go to that later. But calling an annotator bad, that's also problematic because you are saying that a person shouldn't be thinking like they should, like they are. So we are running an experiment that we are saying, okay, your opinion doesn't count because it's not the same as the majorities. Imagine the world would work like that, okay? So the question is whether this disagreement can be seen as noise, that we should strive for removing it from the data, or it's actual signal that we can use to make better AI systems. So in the old view, you just throw out the noisy items, you just get more annotators that align with your views, or aggregate to a single label. But for example, in the new view, we see that as real information, that we need to model the full distribution, and we need to make our systems learn that there are different perspectives, different opinions on the same data. Okay, so if you are actually smart, and you surely are because you are in this masters, probably, not necessarily, but probably you were that kid, right? So this is a little bit about that. I always make the comparison with these kids, right? So they're usually bright kids. They just don't fit in, right? But what we sometimes do, we just expel them from the class. Like, you are not accepted. Your behavior is wrong. Move out. And that's something like we are doing, or what we have been doing with the annotators. And that's a problem. Okay? So there are certain voices in the AI community that, starting to rise a few years ago. And there is a famous paper by Valerio Basile, who is a researcher at the University of Torino, and who says that it's the end of the gold standard as we know it. And I feel fine. This is a REM song. Probably you know it. And some other people started making papers on this topic. We need to consider disagreement evaluation, or the survey that probably you know about by Alexandra Uma. Also, the work by Barbara Planck at the University of Munich. They are all the time, coming up with new ways to address the problem of human label variation and how to treat it from an ethical perspective and also from a technical one. Okay? So this is the first, maybe the seminal paper by Barbara Planck. And what it comes to say is that the human label variation is pervasive, principled, and a signal wisdom model. That's it. Okay? And she identifies like 3 sources of variation. So for example, the stimulus. So this is the text, for example, you read, and it can be ambiguous, like the examples I showed you. Those are inherently ambiguous. You cannot remove that. They are inherently ambiguous. Or maybe they are missing context. That happens also a lot in STS because you have very short sentences and probably you don't have enough context to disambiguate them. Yeah? Also, you have the annotator. I already told you about this. They have different backgrounds, different perspectives. Maybe they were tired that day as well. And also the context. So, for example, how you design the rubric or what specific instructions you give to the annotators to go through your data. And this has been applied in several tasks in NLP. So, for example, NLI, and here the work by Bablik and Kwiatkowski says that up to 30% of items have multimodal label distributions when re-annotated. So they took the original NLI examples, so natural language inference, and they said to other people, okay, let's now re-annotate them, like we did in our experiment. And they saw that what distributions changed and said, well, it seems that 30% of the original items that we thought were crisp, they are not. Surprise. And post-tagging, even post-tagging, which is mainly lexical task, like there is no much room for disagreement, there is 5% systematic disagreement on edge cases. So for example, this would be gerunds and specific particles. But this is a lexical task. And also there is 5% systematic disagreement. That wasn't considered. Of course, sentiment analysis or hate speech, that's what might be offensive for me, might not for you, okay? And also that changes according to the annotator demographics, the country of origin, the gender, race, etc. And there's a lot of work on that as well. This is the paper by Valerio Basile, and what he comes to say is that, well, for many NLP tasks, there isn't a single truth. That's it. Like, there are many. And we need to actually embrace that rather than keep trying to remove it, because AI systems just cannot go farther than what we are doing now. We need a change in paradigm. It doesn't mean, and this is something that I want to leave very clear, it's not that all these people did it wrong, but it's more like a paradigm change is needed in the current situation. Okay, and this is what I was telling you about. You might all distinguish between 6 sources of disagreement. So they have the two of them can be interpreted as noise. So for example, what I said, the annotator error, the annotator doesn't understand the question or mistypes even the text and does it wrong. And also the sloppy annotation, this happens a lot. It's becoming also a problem in crowdsourced experiments because like people would use an agent these days to do the annotator for them, and they will get the money. And that's also a problem that we are trying to control. And also, it's just people who just will click the A question or the first one and go through the examples and just get the money. But there are certain techniques that can be put into place to avoid these kind of problems as well. So those two are more or less addressable, but there are the other 4, like the ambiguity, I already told you about this, subjectivity, missing context, or multiple plausible answers that those cannot be removed. Like ethically cannot be removed. You need to embrace them and incorporate them into the training. Okay. So what we did, well, as you saw, this was done on natural language inference, hate speech, toxicity, and we focused on the semantic textual similarity because this was something that nobody had done before, like looking at the disaggregated scores from the annotation experiments. So, and we tried to look into what happened there and see if we could train better similarities, systems for semantic similarity. And this is the story. This is my story. And I hope you like it. Okay, let's do a little bit of a detour. I told you that it's a problem to average, to calculate average values from ordinal scales. Why? Because the main problem is that when you do this, you are interpreting or you are assuming that the points in the scale are evenly spaced. So the scale is a metric one. And this has been done typically due to, well, for convenience, because it was easier to do it in that way. But if you look at the field of social psychology, for example, and these guys are really good at statistics. They're really good. They have been using them for much longer than us. And there is a recent paper that I will talk to you about that started analyzing papers published on very reputable sources and that used ordinal scales as metric. And they found a lot of problems, okay? So what you need to have clear is that ordinal scales, you cannot compute a distance from them very easily, okay? It's not a kind of measure that you can do those kind of operations, okay? This is known since this has been known since the 1940s, okay? But this is basically what you need to stick in your head, okay? You cannot meaningfully average ordinal data. As you saw before, we got an average value of 2.4. What does that even mean? Like, if you get one person who said 2 and one person who said 3, what's that? The person in the middle? Who is that? It doesn't exist, really. So we are committing little statistical crimes every time we do this. So, but we could think, well, it's fine. We have been doing it for years, decades, and we almost achieved AGI by now. Great, everything works, or not. Maybe we are going in a direction that we shouldn't be going. So let's see why I think this might be bad. Right? What could possibly go wrong? Right? What's the problem? No problem. Let's continue doing the things in the same way. And this is what Liddell and Krasky, these are people, very reputable people from the field of social psychology, which is very close to HCI, by the way. So these guys took a lot of, as I said, a lot of studies published in very reputable sources. and then they reanalyzed them. They ran the statistical tests, assuming that the space in the ordinal scales was not even, okay? And so instead of using, ANOVAs or t-tests or this kind of parametric statistical tests, they used ordinal regression, basically. I don't know if you have used ordinal regression before, but it basically assumes that these intervals are, like the annotation experiment is like a hole in a black box, and you see like a part of the continuum that the people are modeling. So in this case, it's the semantic similarity. So you have on one side, you have something that's completely similar, and in the middle, you have a line that you see only through little holes, right? Those are the numbers in the ordinal scale. But you don't know where those numbers are placed. You just know that the 1 is less than 2, and 2 is less than 3. That's it. But you don't know exactly where it is. So ordinal models, they don't do this assumption. They just work differently. And what they found was striking. So they found that in these journals, the 100% of papers used metric models with ordinal scales, 100%. And what they found was a very high rate of inflated false positives. So in terms of medical terms, this always, I always like to put it in medical terms because it sounds more shocking. In medical terms, it's like you are giving some, like a medication to someone, and you feel like it's working, when it's not. Okay. Also false negatives, and also inverted effects. So what you think was going to one side actually went to the other. Very dangerous thing, right? This is social psychology, but I can tell you that in other fields, it happens the same. Okay? And if you start looking, this is like number 23, that film by Jim Carrey, that he starts looking, seeing the number 23 everywhere. He looks. And now, if you start looking in AI evaluation and NLP evaluation, you start seeing ordinal scales everywhere. They are everywhere. So in STS, of course, but sentiment analysis and also the preference data sets for reinforcement learning, they are also ordinal, a lot of them. And we have been treating them as metric, yeah? Also for machine translation, summarization, image captioning, whatever. So anything you, and at any moment that you're trying to elicit dimensions like fluency, consistency, these kind of things from humans, you, like most part of the times you are using ordinal scales because they are very convenient, much more than doing contrastive learning because you need more combinations to do contrastive. So it's cheaper. Okay, also there are, well, it's not that ordinal scales are perfect. Also, there is this study that a reviewer sent me once that basically says that by the way, like the disagreement in ordinal scales comes naturally in the middle of it. It's basically, here you can see this is for concreteness, okay, it's the dimension of concreteness in annotation study, and you can see that the disagreement happens more naturally in the middle. Just because, you know, you are more likely to disagree there. You have more choices to select from than not, for example, if you are in the extremes. Like you only have one option to disagree with a 5 or with a 0. Okay, so there are also these kind of things that we need to treat. Okay, so very bad. What's the alternative? So if in our experiments we cannot aggregate by averaging, so what we would do? So we need, first, a way to measure agreement that respects the ordinality, that takes into account that all these things, that disagreement can happen more naturally in the middle, that the ordinal values are not evenly spaced, etc. And also we need a way to train and evaluate our models with that. Okay? And for that, I'll show you a few metrics and techniques that we have been using. And for this, Krippendorf is the guy, okay? This is, I've been kind of like in a romantic relationship with this man for some time. I've been showing the photo for some time because he was a boss, really. Originally, he had all these, you know, well, he considered all these problems like many years ago. It's just that he was like kind of like forgotten. And sometimes like Krippendorf's alpha, which is a measure of agreement, kind of robust, very robust. It's, well, used just to justify that your annotation experiment is okay. But there is more than that. It's like, it's as always, people just want a shortcut. And they want to run a metric on their data set and say, oh, succeed, continue. Okay, so they just want these okay messages from someone. Okay, but this guy did a lot of things, actually. So going to the actual case, this was the paper that you probably read. And I'm going to tell you how we applied what we learned from Krippendorf in this paper and how we could use his teachings, to propose a solution for the problem in STS, which had typically a lot of problems. So like years ago, people already knew that STS systems that, by the way, they powered the AIs that today are giving us embedding systems that are used for information retrieval. So for example, retrieval augmented generation is based on systems that were originally trained with this kind of data. Because these are like cornerstone tasks in NLP, right? So we'll see what problems people were identifying before we published this paper, okay? Before that, this came to our mind because we were in this project about semantic similarity in song lyrics. Okay, this was a study that we published at Zeppelin in 2023. And basically, well, we examined some biases, some certain tendencies that people annotating the songs were displaying, which were not good. So for example, we saw that the text length, so the length of the lyrics of the song have an effect on the perceived similarity. So there is a bias there. So this original wasn't controlled in STS. It's true that sentences are very short in STS, and they didn't scale it up. But there is certainly an effect there. And well, the most striking finding was this one. And basically, we were annotating like the similarity using a very similar rubric for the song lyrics. And I saw this. And these are the real annotations and the scores that a system gave to pairs that got a modal value of 0, 1, 2, 3, 4, and 5. Yeah? So for the 0, you can see the systems we tested the data with. They had this level at a much lower similarity than, for example, all this. And this was like, oh, so the interpretation was, so there is a jump. There is a quality jump between 0 and 1, a bigger one than it is, for example, from 1 to 2 or 2 to 3, because of the way the rubric was made. And yeah, I was puzzled at the beginning. I was like, so why? Like, right? The scale should be constant with the similarity, more or less. You should see like a monotonic, increasingly monotonic similarity if the systems were working well. But this jump was not what I was expecting to see. So fast forward, I started looking in the original STS data, and I got acquainted with how the task worked. And basically, yeah, I saw that typically STS systems were evaluated using a Spearman rank. Basically, they computed the averages from the annotation experiment, and then they did this rank using a Spearman rule. Yeah. So I continued looking at the data. So I got the original STS data was done by people from the HITS group in the Basque Country, Eneko Aguirre and some other peers. And I went to a webpage because they didn't release the disaggregated data. So it's like whenever you go and knock at some doors and try to get the disaggregated data, they just won't reply, or they will ignore you, because sometimes there is a problem with, and I'm not saying that Eneko did this, but I know for a fact that other people did. They don't want to unveil what they did with the experimental data. So they won't give you the data. They just said, no, we aggregated like this, and trust me, this is the ground truth. And this happens a lot. This is very typical. I can understand the reasons, because I've been there too, But yeah, luckily, if you go to ICSA's group webpage, you can see that there is a link there to the disaggregated data for the 2017 STS task, the semi-eval task. So I downloaded the data and started looking at it, looking at Perl scripts that were made in the 2015 or around. It was a really nice, fun experience. I recommend that you do it once at least in your life. And yeah, I could go through the whole process, right, and how they did this. But basically, they did this pre-aggregation, and they removed low agreement pairs using a metric scale. So they did like these two wrong things. They did them in this data set. So basically, yeah, said, okay, this pair has a lot of spread. We just won't include it in the final release of the data. This pair is discarded. So it's like the kid that's sent to the corner. Like, you are a bad annotator. You shouldn't. You are not worthy of being in a gold standard. And then, yeah, like they used mechanical Turk, English speakers, Western origin, etc., etc. And the domain also was, this was public. The domain was news, image captions, and others, but there were no other domains, like, for example, legal or medical, which is a problem too, although there have been extensions of the original STS task to other domains. But this seminal system only used a few of them. And that's it. I could look into this script and see some problems with that. But my intention, as you will see, was to employ the whole data set at this, like without being aggregated, as you can imagine. Okay, so here is the fact that, for example, some people already had problems with STS. So, for example, here, I don't know if you know Niels Reimers. This is at the UKP lab. They were the people who created SentenceBird, for example, and they obviously this is very related to STS, and this was by the time they released these models, and they were looking into these issues too. And for example, yeah, they said like usage of the person correlation is common practice despite the fact that Aguirre et al. State in the discussion of the results of the same eval. So this is the first STS task about STS. Evaluation of STS is still an open issue. And surprise, in 2023, still is an open issue. So it's far from being resolved. And also, well, we are preparing a paper, right, with that basically it's a critique of person correlation because, yeah, it's probably not the right way to keep evaluating AI systems. So other alternatives need to be considered depending on the requirements of the target application. Also, there are two factors defining the quality of intrinsic evaluations. The used data set with the human judgments on similarity and the used evaluation measure to compare system outputs with the judgments. So this was a long time ago, but nobody seemed to care. Like we, keep pushing the lever and churning out systems one after another, and they work, and this works, and this happens all the time with modern AI systems and modern benchmarks. It's like you can see there is a misalignment, right? You see AIs performing or LLMs performing really well on one benchmark, and then you use them or use them in another similar task, and they don't work. So why is this? Because there are many decisions, many design decisions that are put into place to create these benchmarks that are just forgotten once maybe the paper is published. So this has been a long discussion in the NLP community. This has happened for years, and it will continue happening. Because basically, when you are creating benchmarks, you are consciously giving an opinion about the world, about what the truth should look like. And people not always disclose this in the best possible manner. And we need to be open about that and disclose it, because it's good for the environment. Okay? For example, accuracy is also a common evaluation measure for many tasks. However, as the STS scores are continuously valued, it is unclear how to compute it. So they were already saying, there is a problem that these scores are on a continuous scale. What does that even mean? And why are we even using accuracy for this? Like, what are we aiming to obtain? What are we aiming to that our AI system should strive for, should interpolate for? So, and then you could see these kind of things, like the ranking of the STS systems according to the Pearson correlation was on average 19 positions different than the ranking according to another metric that it's more like NDCJ. So depending on the metric, you could see that there were things that were starting to jump around and didn't make a lot of sense. So yeah, we decided to go to and search for the original data. So it's actually, the paper was going to be called Show Me Your Grades in the beginning, but we dropped that idea very soon. But here you could see like the English trials tests, row annotations and Perl scripts. When you see this, it's gold. It's internet gold. So if you ever see that, just download it, just in case they remove it. Okay, and this is more related to another problem with the annotation experiments, and it's that I'm always trying to bring concepts from social psychology, cybernetics, these kind of things into NLP. Because I think that in a manner, the experiments that we do with AIs, they are also social experiments if you look them from another perspective. So we could be analyzing ourselves from the perspective of the AIs, if you think it differently a bit. For example, Krippendorf says that there is a 0.67 cutoff So you need an alpha of 0.67. So the task is good enough to even run an experiment. So to continue analyzing the data and obtaining significant results from it. What happens if you go, so here, sorry. Oh. So if you analyze the original STS data, you can see that pre-filter, you have like values much lower than that. So what we need to think about is, so we are training our AIs with data that wouldn't even be valid for a simple, not simple, but for a social psychology experiment. So we cannot derive actual conclusions from that data, and we are just using it and we don't care, basically. We just feed it to the AI and it will make sense out of it, maybe or not. Okay, so in the end, when we opened that data set, we saw that remember that STS-15 data set only contained 3,000 pairs that were already filtered, aggregated, all these kind of things. But originally, they have almost 8,000 pairs. So a lot of data, valuable data, was dropped in the process. So also a lot of money that was like thrown away, right? And also many people were discriminated. As you know, we had 5 annotators per pair, almost 40,000 individual judgments in 5 different domains, okay? Basically, if they hadn't published this data set, we would have no paper, right? It would have been impossible. Or we would have to pay some other people to reannotate the examples. This is something like people in the NLI task did with Chaos NLI. But we didn't have money, of course, for that. So luckily, the IXA group were so kind to put this in their webpage. Okay, a little bit more about the Krippendorf's alpha. There are other measures to, or other metrics to measure the agreement. Basically, what the most used are Cohen's kappa, Fle's kappa, but they weren't good for our specific problem because, firstly, because they weren't ordinal aware. So, like the disagreement between, for example, 2 and 3 is the same as the disagreement between 0 and 1, and we know it's not like that. So we couldn't use a metric that didn't take this into account, you know? And also, we had examples with missing data, which Krippendorf's alpha is robust to. So it was basically the mainstream metric that we could use for this problem. And also, I like Klaus Krippendorf. So that was. So the idea is that alpha actually compares the observed disagreement between what the expected disagreement. And the expected disagreement is computed empirically from the annotations. So it's a frequentist approach. It's just if you know that, also if you observe, that 2 numbers appear more often together, you see that disagreement between those is more common. It's more, you can expect those two to appear more. So the distance between those labels is shorter. So and it's purely data-driven approach. So I like that. I like data-driven approaches. Okay, and this is the other part that makes the one of the aims was to create a distance matrix between the different labels, so you could obtain the real distances between all the elements in the scale that we saw they were varying in the lyric sim experiment. So we know that in the end we wanted to derive something like this, and this matrix is nice to ponder it and wait for a second and and see what the implications are. Basically, it's completely crazy scale because you can see that there is not, it doesn't comply with the triangle inequality, for example. So it doesn't mean that the distance from A to B plus B to C is larger than A to C. So that doesn't happen because we humans don't work like that. We have other heuristics to approach the problem of semantic similarity in this case. So we don't work like that. Also, we can see that here, we also observe that the distance between 0 and 1 is 0.10, whereas the distance from 4 to 5 is only 0.02. So it's 5 times larger. So there is a semantic gap that is larger between saying completely dissimilar to slightly similar, or whatever the one was, and 4 and 5. So those distances, perceptually, in the annotation experiment for these participants, were uneven. So it was nice to consider this in the training of the system and also in the evaluation. So we cannot forget about this. So in the end, this is how it happened. What time is it, by the way? How? 1 hour already. Oh, okay. Time flies. Great. Okay. I'm going to drink a little bit. Sorry. I need to stop. 1 hour mark. So this is the kind of like the preparation of the experiment. And we divided the data by terciles of disagreement. So basically, we split it from more disagreement to less disagreement. And we could compute how much each item was contributing to the global disagreement. So we have something like a per item disagreement. So we know, according to the expected disagreement that there should be in one item, seeing the labels that are in that case, we know how much disagreement we are observing in there. Yeah? And we divided, as I said, like transversally and longitudinally by mode. So the modal value for each one of these cells in this split. Yeah? And we roughly obtain the same, no, at the end. So this is something that we wanted. And here you can see the contingency table. So with all the numbers. So probably once we have this, we had like certain research questions. So for example, does modeling the full label distribution improve calibration? So this is something that changes from paradigm to paradigm. It's, we don't want accuracy. We don't want F1. We don't want to predict the single God's truth of the STS, whatever is there in the nature, because it doesn't exist. You know, there is not a similarity score that is golden, waiting us out there in the nature to be discovered, right? So we are interested in measuring, no, how our distributions are different. So this is more like calibration. Utility cost, so does this hurt traditional metrics like Spearman rho and root mean square error? This means that, well, we included this in the paper. This is a little secret, but we included this in the paper because getting these kind of papers into conferences is a little bit dangerous because most reviewers don't care about this. Or probably you don't either. but most reviewers would say, well, okay, so what? What is this for? Why, you know, because it has certain philosophical implications that not everybody is happy to accept. And sometimes there is reviewer resistance and these kind of things. So we also wanted to say, okay, easy, take it easy. This won't affect your previous metric, right? Just relax and accept that there are many truths anyways, okay? And also, we wanted to measure the trade-offs in the end. It's like, well, if you win on one side, then are you losing on another, or what are you missing, you know? So what we did was a very, very quick experiment. We actually set it up in a couple of hours, running in a couple of hours. So it was basically training Sentence Roberta, which was the state of the art by then in STS. And we wanted to train it using the means, so on regression, for regression, and on our new disaggregated data set. So we recomputed the means of everything. We split it, train, depth, test, and we train the system and test it. But we also wanted to know if there is a possibility that we can reconstruct an ordinal distribution from those estimations. So from a point estimate, what would be the expected ordinal distribution that you will get, right? So we want to know if they are more or less aligned with what would be the center of this distribution, more or less. And for that, we computed the deviations or the spread by tercile that this distribution should have. And then we adopted the other strategy that was, no, let's give the disaggregated data to the encoder, and let's see if we can do something. We have to apply temperature scaling at the end, because the logits in the last layer, they are we have very few data in the end. So also, it was a known problem that you cannot derive directly the probabilities for each class from the last layer. Like we saw problems, and the calibration worked much better in the end. So there was a needed step. Yeah. So this is basically what I told you. So we trained on regression, on the mean labels, and at inference, we predicted the scalar, which is at the center of a truncated Gaussian, and then the variance of that Gaussian distribution was learned over the different slices on the depth data. So there was no data contamination in the end. And then we used a modification of cross-entropy loss, which is very common for this kind of problems, and you probably used it already. That is the ordinal log loss. And there was these guys, I don't remember the conference, but basically they tested many loss functions for the ordinal data, and they found that this one worked really well. We tried a few of them, and our results were in line with these people. So we used the ordinal log loss at the end with a sharpness exponent of 1.5. Okay. So this is the same as it's incorporating in the loss function the concept that there are different distances between the labels in the ordinal scale. Okay, it's just incorporating that in the loss function. So you know that if you are far by 3 points in the ordinal scale, it's worse than just to be 1, for example. But also we plugged in a distance matrix, like empirical distance matrix, to account for those errors as well. So that goes into there. Oops. And then this is the temperature scaling, basically. So it's a way to calibrate the row logits. So we obtain like sensible probabilities in the end from the last layer in the encoder. Right? So as I told you, we evaluated in the traditional way with Spearman rho and root mean squared error, so these two metrics. And then we employed a distributional one. So with the delta EMD, which is the EMD, have you used EMD in the past? Who has used EMD? It's called Wasserstein's distance. So it's basically, it tells you how much effort you need to put into converting one distribution into the other. Maybe in the middle, you cannot see. But it's basically like if you want to obtain this distribution in the end, how much effort you need to put into moving these blocks into the other one, just to make the distributions equal. And this is also a metric that takes into account the distances between the labels in the ordinal scale, which is nice. So this is delta EMD, what we called delta EMD, which is the distance matrix derived from Krippendorff's alpha. Yeah. So this is the intuition. It's how much work to reshape one distribution into the other. And the standard EMD doesn't use a distance matrix. So we used the distance matrix because we know the distances are not the same. Clear? So in the end, as I told you, we need to evaluate the systems. The systems trained in the soft manner, so using distributions, we need to test them in the old paradigm. And the systems trained in the old manner, we need to test them in the new paradigm. So we need to convert a distribution in a scalar. This is very easy because you just need the expected value for that distribution, and that's it. And for the other one, we use this Gaussian thing that I told you. You have more details in the paper. I won't stop a lot. But the results were, you can see them in this table. So basically, we saw that the soft approach, when not calibrated, it was really bad. So we were obtaining like the bad probabilities all the time for all the labels. So we had to calibrate it. And we saw that basically we were performing better in delta EMD, in root mean square error. So this is the new way and the old way. And we obtained better values in the disaggregated data. But we also tested with Spearman on the STSB, which is the official data set for STS. So STS benchmark, it contains all the data sets that were released through the years in the different semi-eval tasks from 2012 to 2017. So all those years. And they took the best of the best. So the more, the more crisp and clear examples, they are in STSB, in this benchmark. This you can see it in MTEB, so the benchmark for embeddings. It's still there, so for example. And we could see that training with the original data still gave you, this is kind of expected, the best value on that data set. But when you test it with aggregated data from that wasn't filtered, it obtained the worst score. So basically, we could see that the baseline, which is trained on filtered data, does not respond very well to data that's disaggregated, or even to mean, to estimate it on regression mean values that come from disaggregated data. So you cannot use those old systems for this. They just don't work the same. And this is very, very small data. So because we didn't have more data. Now we have more data. and we are running more experiments with this. But this was a pilot study. You need to be aware that this was also done without the approval of anybody. So we didn't have data, and we didn't want to ask for data because we didn't feel like so. Now we did, and now we obtain more data, and we will be testing more this new paradigm with disaggregated data. But it's nice because you can see that how the design decisions that were put into making these benchmarks that are the cornerstone of modern NLP, they affect everything that comes after. And so yeah, that's it. And we could also see that the hard system, so the truncated Gaussian distributions, so estimated ordinal distributions from these point estimates, more or less work, specifically on certain slices that contain distributions that were Gaussian, exactly. So they were unimodal. You could see that in the previous example, when in the experiment that we ran live here, we could see that some distributions were really unimodal. Like you could see that there was a peak value, and then in the sides you get a little bit less, and the farther you go, the less people chose those options. So that's unimodal, clearly unimodal. And I can tell you that most part of examples in STS are like that. Well, most part, like a majority of examples are like that. But in other parts, it's not like that. So in other parts of the data set, it's less than that, and you got more, for example, bimodal distributions. So you have opposing views of perspectives. So you have a lot of people in the 2, a lot of people in the 4, for example. And you have clearly two opposite views. Okay. So yeah, you could see basically that the baseline, which was trained on STSV, it's our models on that Spearman. But what does that even mean? No? So to close today's talk, I want you to reflect on the broader implications that can be derived from our study, and is that the benchmarks encode many invisible choices, and also that the calibration is probably the right approach to measure whenever an AI system is able to reproduce the opinion of a population of humans. So basically, it depends on the task you are applying your AI. But sometimes you want to tune your system so it behaves as exactly one single person. But sometimes you want the system to behave as a population of people. It's not the same, and we need different approaches to that. Definitely not just one. And also that uncertainty is information, not a bug, but there is also a problem. You could say, okay, but we are training with a lot of uncertainty, with a lot of information, and we are making our systems way more complex. This is, in HCI, is what's called, well, and in software design is what's called encapsulation, right? So you don't expose too much of the inner workings of the system, so you don't overwhelm the user. Sometimes you just don't need to know all the different perspectives or all the different views that people have on a certain topic. You just need one average answer, and that's it. No? That's what's useful. But sometimes it's not. So it depends. It depends on, on what the AI is being used for. But if we only use one paradigm, then we have a problem. Our evaluation is misaligned with the tasks that we want to use our systems in. And this is very clear for me, and I am ready to die on this hill for this, and it's that ordinal scales need to be treated with ordinal tools. So don't average. It's not correct. It's not correct by any means. Sometimes it can work, because it could turn out that the differences in the measurements are, or between the ordinal values in the scale, are metric. But it might be a coincidence. It might be that you don't have enough annotators. And if we keep doing it by convenience, then we might run into problems. So if you can, just don't do that. Don't average ordinal values. It's not correct. And also, here we see another problem that's coming. Maybe you've read this paper or you've seen it, that ChatGPT outperforms. This was released in 2024 or around, and there was this famous paper that said, oh, now like ChatGPT can create annotations like humans do, and we can replace them. And now we have like 2 years fast forward. We have LLM as judges, and we are, training more AIs with data that was annotated by other AIs, and what could possibly go wrong, right? Maybe something might go wrong with that. Who knows? Who knows? But here they say that the zero-shot accuracy of ChatGPT exceeds that of crowd workers for 4 out of 5 tasks. So when I read this, I was pulling my hair out. I was like, what does it even mean that they exceed? That they exceeds the accuracy? What accuracy? What are you even talking about? Anyways, but we know for a fact that probably, well, this was written by an AI, so never mind. Okay, that's a reflection. But now LLM as judges are useful, right? They might be useful, but we are still looking into them, right? We are trying to comprehend how they behave. Maybe they cannot replace us just yet. Okay. So future work, so from the paper we said, yeah, expand it to ordinal tasks, so other architecture, maybe annotating with bigger LLMs and see what happens, and also open problems with STS, so systems that perform very well on STS, then you go to retrieval tasks and they fail miserably. Why that happens? Because, well, who knows, maybe the evaluation is wrong in the first place. So maybe a tuning system in this manner leads you to better retrieval systems or more personalized or, these kind of things. So this is an open line. And also the elephant in the room, what I told you earlier, that reinforcement learning with human feedback is basically done on preference data sets that are annotated on ordinal scales. On my tests, some of them show that the scales are more or less metric, but they only use 3 annotators. So the experience tells me that when you add more annotators, you get more problems to see that metric-like behavior appearing in your data. But that's another problem, that we are annotating data with just 3, 4, or 5 people and call it a day and say, this is enough. Why is enough? Also in psychology studies, you don't run studies with, or experiments only annotating with 5 people. Imagine a medicine or a medication, for cancer that was only tested with 5 people, no? It is an exaggeration, but you see what I mean. It's not, there is a famous paper on NLP that says that the majority of NLP experiments are underpowered statistically. So there are many things to change before we reach AGI, maybe. So in the end, is this all worth the effort? So I like this sentence by Bertrand Russell that says, the whole problem with the world is that fools and fanatics are always so certain of themselves, and wiser people so full of doubts. So maybe we want to create wiser AIs that, well, they are a little bit more doubtful and don't believe that there is just one single truth that we should all follow blindly, no? Maybe. Okay, so thank you for listening. And I'm happy to take any questions if you have.
Alejandro, for your talk. It works, yeah. Thank you for your talk, and also for coming to Pamplona, for giving us for your talk on disagreements. So now it's time for questions. Do you have any questions? Yeah.
Thank you very much. I have a question with the dataset at the start. Dataset, you took it and you divided it based on the disagreement, I think, into 3 different groups.
Yeah.
And for each group, you created a different Gaussian, different distribution to then take the scalar prediction and to get the distribution from that.
Yeah.
But in the paper, I think this could be problematic when new data came in, since you did not know exactly in which group that both pairs would land on. Mm-hmm. And instead of just predicting, maybe with the 2 different texts, in which of the 3 groups that data lands, have you thought of any other way of predicting or getting this distribution that does not, that it's not limited to just 3 different groups, and maybe it's more granular or more continuous in between all 5?
Yeah, that's an actual problem. That's a very nice question. The thing is that there is a long way still to put this, I think, these systems into practice. We didn't have enough data, but maybe we could derive like estimations, like more accurate estimations or more granular estimations in the end if we had more data. But yeah, this is a problem that was raised by one reviewer, and basically, yeah, I think that we should get, like, we should have more data, more disaggregated data, and see what happens. Because currently, I couldn't think of any other ways to put this into practice. So I haven't. That's still another problem for me. But do you have any ideas? Just let me know.
Okay, thank you.
Cheers.
My question was kind of similar to Lander's, and was, why did you decide to split it into even groups instead of defining like some ranges or some values with the alpha?
Some values.
That's
That's what actually was done. So basically, we wanted to have, in the evaluation, we wanted to have bins that had the same number of elements, because otherwise the comparisons wouldn't be fair. So we wanted to obtain a data set that was balanced in that manner, because, but basically what we did was compute the per item alpha for each one of them, and then just put it into 3 buckets. But the main idea was that that these buckets were balanced, so they were comparable.
You said that most of the datasets are annotated by 3 or 5 people, and so do you think that maybe that's the biggest problem here in tasks such STS or NLI? Because even if you predict just the mean or you model the disagreement, you are relying on just the point of view of 5 people, and maybe it's not representative enough, that?
It's really not representative enough of anybody. That's actually the, sorry, I'm gonna close the door because I'm a little bit deaf. So it's definitely not representative of anything. And I think I've been telling you this during the presentation, that we just don't have enough data in this manner so we can analyze how different people think about a given task. So what's going on is that you are being actually aligned with a majority of people that is not representative of your culture, of your ideals, of, you know, so, and this happens with reinforcement learning and more. So now they are thinking, okay, we created these massive AIs on the preference of a few people, and now we are, like, I went to last ACL conference, and there was this woman, there was at the head of Google Brain or Google DeepMind, yeah, and they were really concerned about the alignment, right? Alignment, and said, okay, it's very difficult to obtain the alignment because you didn't invest enough money into, you know, having these data sets. And this is the main idea that, for example, you know that only with 5 people in and 6 items on an ordinal scale, you are having a very high relative error. I can give you figures to show you that. And the estimation in other fields, like for an annotation experiment, is that you should go north of 18 to obtain significant pairs or items. So you know that those scores are significant. So, but there is always this trade-off, no, between how much money you put into annotators and how much money you put into different items. There is a paper also that discusses that. I can send it to you if you want. But yeah, it's definitely like it is working now. I think it's just not enough. We'll see. Maybe if we have the power to, you know, create our own AIs in an open ecosystem, maybe we, like some people in the country, here in our country, are doing it very well. No? They are creating AIs that are more aligned with their principles or their culture, and for that you need to invest money into actually getting to know how the people in that region think about something. So yeah, it's definitely a problem.
If we model, as you did in the paper, if we model the annotator's distribution and not use the mean or whatever, so how do we deal with actual like annotator errors, like clicks or something like that? Because we would be modeling the ambiguity and the like discrepancy between the annotators, but also the actual human errors. So the model would be penalized for not making mistakes like a human.
Yeah, yeah. That's a nice question too. Sometimes, well, you probably heard that making mistakes is human, right? Actually, we are running an experiment with AIs and teachers. I cannot tell you much more about that, but we have been observing that professors at the university, they believe like that the AIs that perform worse on the exams, they are more likely to be human. So they mistake them for humans more often. If they are too perfect, they say this is an AI. It's not. It cannot be a human. You know? So the worse it performs, they mistake it for human. So it depends. as always, it depends, because incorporating the way in which a human would fail, it can make sense, but for other tasks that do not strive for accuracy. But you need to bear in mind that doubting, this is the sentence by Bertrand Russell, doubting is very human. It's the most human thing there is, probably, at least for some of us. And sometimes it's good to have doubts and to reflect on the implications of what you're doing or what you're seeing or whatever. But incorporating that into an AI could also make it make more mistakes in the end. So it depends in the end if you want what you are using the AI for. So this is why, for example, the pre-training days of getting the whole internet and turning it into a model for pre-training are over. So people from all these labs now are actually doing what we did with STS as well. They are looking a little bit more into the data, and they are filtering the data. So this is very common nowadays, and it gives you better results. So, but yeah, I think this is a very, very philosophical question as well. That a nice philosophical question is like whether if we want to build AI machines that doubt as humans, and what for? And find a use for that, if there is any. But for example, I was at the last Sky conference, and there was this nice paper of one guy who had this Socratic AI. So it was an AI that was fine-tuned to not to tell you the truth, but to make you reflect about your own ideas. So it kept you trapped into this epistemic hole or whirlpool for days. It was the aim. But it was really nice, and there are already people who are thinking about it. But this is a really nice question. Thank you.
Hello. In the results in the table, I saw that, for example, for certain slices, the error, for example, using the hard labels was lower than the soft cal, but for others not.
Yes.
Maybe could it be interesting, like using like a routing or something that uses like one model for certain slices and the other for the others. I don't know if I'm explaining well, but.
Well, the thing is, as I said, we need more data. Those numbers were run on a 5-fold cross-validation, so they are significant, but not that much, or not as much as I wanted. But it's more like the results also explain how the data set is. So if you know that the hard model performs better on a certain slice, it's because more examples in that slice are unimodal, because you can approximate them using the truncated Gaussian thing, And if the other performs way better, is that like there is more disagreement. You can see that in some slices, the soft model performed better, and it's probably because it was learning like these bimodal things, which occur more naturally in there as well. So as I said, yeah, we need to find use cases for this and say, here, learning the disagreement is good, and here it might not be good, So, but this is a very, very seminal thing, and we are still working with this. But yeah, that's probably something that we could, have a switch and say it's solely going to be oriented like towards that. It's like here we don't need the uncertainty. Just start thinking in this mode, like I don't know how you would call it, no doubts mode, and you just strive for the ground truth, right? And then switch it, and now you are you have more doubts. No, there are some neuroscientists who say that the brain might work like that with two modes. There is this nice book by winner of the Nobel Prize, Daniel Kahneman, that is thinking fast and slow. So sometimes, there are some people trying to map like neuroscience and psychology and all this to AI. So maybe we need those two modes too. I've been thinking about that lately. Yeah. Nice, thank you.
So my question has mostly been answered, but I would like if you could expand a bit. You showed that in the STSB benchmark, which is very filtered and very curated, the original baseline performed better. So I wanted to know your opinion if even nowadays the gold benchmarks are very biased and they have been filtered to remove the ambiguity, and due to that, these soft approaches cannot really get good results, and we have been getting overly optimistic results with the point estimate approaches. And what would be needed to change this?
Very nice question. I think it was a really good summary of my talk. I really like it. Thank you. Yes, what I think it would be needed to change, probably that the young people start adopting these new paradigms and start thinking beyond the averages, beyond the point estimation, beyond obtaining a single better system on a leaderboard that is composed of a few tasks made by other people. Maybe you need to start creating or crafting your own data sets and evaluating systems on your data sets than by you or by your community, for example. Or maybe we need to put less money into GPUs and more money into people, for example, or annotation experiments, because that also would give them jobs, which is nice, no? That everybody has a job. It's a change of paradigm. It's a change of the way in which maybe everything should work. But I don't know if there is an instant, a clear path. I don't see. Maybe it's this. Also, it's like that. Is that also explainability sometimes is good. It's good for not only having the scores in a leaderboard and saying, oh, I created the best system because I overfit it to the leaderboard and I won this competition. That's nice. Probably like the advancement, the technical advancement you put into place was nice, good. But sometimes you just need explanations. The more bigger the systems grow, the bigger the systems grow, the less we are able to explain how they work. Sometimes maybe I feel that we should sit down and try to explain how they behave the way they do, and so explainability might be a good thing to work on in the future too. That's it. Thank you. Yeah.
I have a question related more on the data sets that you train with that. As same as you say, depends on where you're born, you have a different perspective. Also, when it passed 10 years, do you think the perspective changed and this type of data sets need to be updated of
sure.
the local?
Yes, definitely. That's also one problem, right? That I don't know if you saw the paper of, well, I don't know if it was a paper, but it was this guy who trained an LLM with data up to 1930. Did you read this news? And then he was trying to infer the discoveries that came after that date. So, but he had this knowledge cutoff in 1930. And I tried it. I tried this LLM, and it was horrible, I can tell you. But it was a nice idea. Maybe we need more. I really think that we need more diachronic studies in NLP and in AI. Sometimes it's just, you just have a short time span that we are covering in the papers. It's like, oh, we got over the last guy who was on top of this leaderboard, and that's it, and we won. And this is the state of the art. But all the others that came before, they are forgotten. But sometimes you are missing the bigger picture. as well. You know that you are missing a lot of things if you don't see like the trend in time. So yeah, sometimes it might be like we might be missing these kind of things. And also, of course, we need to update the data set. We need like to put more people in the wheel of the evaluation wheel and see if the systems need to be updated or not. Also, I think there is a problem with how the population, like the people are sampled from a bigger population, like a country or a region, like to do the annotation or to do these kind of experiments. Firstly, it's underpowered, but secondly, I think it's not done in the same way as, with enough rigor as it should be done. Just to make sure everybody is covered, everybody is included, and nobody is left out. So we need to put more into that as well. But yeah, that's a good question. Thank you.
When you were talking about the problem of assuming the metric, the distance between the labels when we have ordinal problems, you talk a lot about the matrix or that half matrix with the distance. Is there like a standard criteria to stating the values between the labels? Because in different problems, or if you ask different people, they may think that some categories of the labels are closer or farther apart, and that could affect a lot to the calculations and perhaps the results.
Well, but that's exactly what we did, no? So the matrix is to account for the varying distances between the labels in the ordinal scale, right? So we need to, that's run like entirely driven by the data. So it's totally frequentist approach. But there are other approaches. There are other metrics that also compute these kind of things, and that might be more adequate for the problem. But we are, like, the main aim of having that matrix was that working on the assumption that ordinal spaces ordinal scales are not metric, and the spaces might, like, the distances might vary. So the thing is that this, as I said before, this can change a lot between tasks, experiments, rubric. So it might be costly to implement it, but still I think it's worth a shot.
But would you think that maybe enforcing guidelines so it is more similar between problems would produce like a bias on how the annotators approach the problem?
Yes, like the thing is that you cannot understand an annotation experiment without the rubric. So there is no one with the other, without the other. Everything goes hand in hand. So every time you're writing a rubric, you know it will have an impact on the annotators, and that the bias, different bias will be taking place. We saw some, like that, for example, in the middle of the scale, like disagreement is more natural, it's more likely to happen just because it's in the middle. But also, for example, we are seeing this in LLMs, but also happens with the people. Like, some people never use the extremes of the scale, or some people just compress it much more, or some people just use a part of the scale. So they use 0, 1, 2, 3, but never go north than 4 for some reason. For example, we know that safety alignment in LLMs actually avoids them to take the extremes of the scale because they are extreme positions. So the safety alignment influences that as well. So yeah, you cannot have you cannot have one without the other. You definitely need to think more about the different kind of biases, and also I think it's important to get people on board that have been doing this for many years. And I'm talking about people from other fields, social sciences, psychologists, these kind of people from more humanities sides. They have been doing this for a long time, and maybe we should get them on board more often. Thank you.
Okay, one or two questions more maximum. Yeah.
Yes, most of the examples you have put at the start are from the natural language processing, and I was wondering if there are any kind of studies or related investigation in other fields that account for the annotation disagreement, like image representation, object detection, that you have to pick an image in the photograph, and that could be like a huge also field of annotation disagreement.
I'm going to tell you a secret. The disagreement and the learning with disagreements community really didn't start in NLP. It started in computer vision. There was a strong community there who started, it was from the image captioning, I think, task. It was kind of like in the middle. And that was the start of it, like the seminal investigation. So yeah, computer vision. So if you pull the threads, you will reach that. I think I can. If you are really interested, I can send it to you. Or yeah, but it started in other communities, and I think now it's spreading more to other fields of AI. Luckily. Thank you.
Hello. So I think that it's really rich and useful to consider all disagreements, but in many tasks we need at the end one decision or one value, like for post tagging or for question answer making decision or for sentiment analysis. So do you think that it remains useful to use this approach of modeling disagreement in this kind of tasks without, because at the end we need to collapse the values into one value without losing the benefits of modeling disagreement.
Yeah. That's a good question. I believe that, well, the first thing you need to be aware of is that there are two kinds of uncertainty. There is like aleatoric uncertainty that happens naturally in the nature and you cannot measure it. It's just, you just don't know for sure what a value might be, but it's only because it cannot be known, right? And then you have the epistemic uncertainty, that is something that if you keep investigating, then you will reach the truth, right? But sometimes that doesn't mean it's obvious. Like about one phenomenon, you can have one opinion, I can have another one. That's how science works most of the time. And still, there is something that is true, that it's objective, that it can be measured. And I said, using the language I used before, it's something that is out there in nature waiting for us to be discovered. But in other tasks, no. So, but still, I think that also in tasks that are about epistemic uncertainty, so for example, the sciences, when you are investigating or researching a topic, no, you are like digging for the truth, right? But sometimes it's nice to approach it from different perspectives. So if maybe we can, in those situations, it's nice to have some doubts, right? Or some uncertainty as well incorporated into the AI. I don't know, but certainly we need to, there are tasks that are subjective, for which there is not a ground truth, and that's it. And that needs to be clear, and we cannot derive a ground truth. It's bad for everybody. Kitties are killed, etc. So we shouldn't do that. And there are other tasks that, yes, we need to approximate an exact answer because we know for a fact that there is one. Then, yes. But still, sometimes it's not that clear. And in those cases, I think it's nice to incorporate uncertainty because, as you saw, in traditional metrics, our system did not perform worse. If you learn better the distributions, obviously, you can estimate better the mean, right? So you can have both things, I think. And having both things is good. So let's try to do that. Thank you.
Okay, so thank you for your so clear presentation, so clear questions and answers, and very interesting topic. I think a lot of discussion, which is also nice to see. And yeah, so thank you. And
thank you,
with this.